This is our ECCV paper, NeRF MAE, Masked Autoencoders for Self-Supervised 3D Representation Learning for Neural Radiance Fields. This work is a joint collaboration between Toyota Research Institute and Georgia Tech. NeRF MAE enables large-scale 3D pre-training using NeRFs as the input modality. It has two components, a pre-training stage and a fine-tuning. Pre-training stage starts with posed RGB images and learns transformer model weights. The goal is to reconstruct masked volumetric patches from an optimized NeRF. Once pre-trained, the encoder is used for effective transfer learning on many downstream 3D tasks. Why use NeRFs for 3D representation learning? Neural fields' emergent properties have made them suitable for tasks beyond showcasing higher rendering quality. Prior approaches have successfully applied neural fields to localize language queries in 3D, infer-accurate geometry, open world manipulation, and efficient data storage mediums. In this work, we show a promising use of NeRFs for self-supervised 3D representation learning. Existing 3D MAE architectures for representation learning operate on point clouds with uneven information density, only model surface level information, and are highly irregular data structures. On the other hand, NeRF's radiance and density grid offers several advantages. It contains information with high density, offers a regular and unbiased sampling, as well as spatial data redundancy. Hence, positioning NeRF MAE as a direct extension of image MAE to 3D. Next, let's take a look at our data preprocessing flow. We start with posed multi-view data. Next, we train an instant NGP NeRF. We extract radiance and density along rays and average the resulting output for all directions. Finally, we mask out 4D patches from the obtained NeRF grid to be used as input to the 3D transformer module. We pre-train a single transformer model for diverse scenes on various data sources totaling over 1.8 million plus images and 3,600 plus scenes. Our dataset mix comprises of scenes from Front 3D, HyperSim, Habitat Matterport 3D, and Scanit datasets. How do we train our model? We utilize a UNet architecture with SWIN transformer as encoder and lightweight voxel decoder connected through skip connection with the encoder. An opacity-aware mask reconstruction objective is enforced for the reconstructed 4D radiance and density grid. Our qualitative results show faithful reconstruction of masked patches to learn strong 3D representations from posed 2D data. Left triplets show some samples from input, masked, and reconstructed volumetric grids. On the right, we visualize the effect of various masking strategies, out of which random works the best. How does our method perform quantitatively? Here, we show downstream tasks comparison with the state-of-the-art baseline, which has same architecture and training method, but with no pre-training. Our pre-training consistently improves performance on both challenging 3D tasks. An interesting result of our method is on cross-dataset generalization experiment. Here, our pre-training has never seen any data from Scanit, yet it is able to improve performance on the challenging downstream 3D object detection task. Next, we show scaling performance of our method and an ablation analysis. It can be clearly seen that our method is able to get better with more unlabeled data and with higher quality input NeRFs. Hence, showcasing strong scaling performance on larger size posed 2D data. Here, we show more qualitative and quantitative comparison. On left, we show faithful reconstruction of geometry for our input data. On the right, we further show that our pre-training requires twice as less data to achieve the same performance as the strong baseline. Here we show some qualitative results for 3D object detection and 3D semantic labeling downstream tasks. One can clearly see our method is able to improve performance over the state-of-the-art baseline with better pre-training. Thank you for listening. Please check out our project page and paper for more details.